Garrett.
Great. Thanks. So thanks for everyone coming out. My name's Jake. I'm a PhD student here on S11, and I'm going to tell you about the work of my thesis. My supervisors are Michael and Nico. So essentially the topic here will be learning from limited experience. We want to reuse as much data as we can to learn efficiently. So there's a couple of the things that I've done in the past, including some of the work here. The thing that all of this work has in common is that it was incredibly tedious to tune and debug and to get working, like hardware, software calibration, all of this. So ideally we can move to some place in the future where we have robust adaptive systems that can kind of cope with the challenges of the real world kind of online, figure out how to solve the problem themselves. And that moves our design responsibilities kind of up a level. This is the level of kind of like adaptive AI behavior we seem to have today. Probably we can do better. So for an outline, I'm going to talk about the problem with navigation that I want to look at, discuss some literature, talk about the questions that we want to answer, and our attempts to address them. So to talk a bit about navigation. Autonomous driving is a pretty popular application of robotics these days, and its navigation is at its core. Has applications to things like logistic robots, and I think this is a robot that's been actually deployed in a hardware store, so it's actually navigating around, the kind of thing that was also done in a museum with the Minerva project in like the late 90s. So navigating systems are out there. This creepy little robot navigates around our own very lab. Now this is the robot that we'll be dealing with a lot of this work that I'm about to describe. It's a Pioneer robot that we actually have in this lab. And the main sensors that we'll be using are visual. So there's an upward-facing camera there that points at this mirror, and that shows you the whole scene. So we mostly want to tackle things with vision. But to look at how we might produce capable robots, we can look at what exists in the natural world. So humans are really capable navigators. We've navigated across the entire Earth. Most of this nomadic navigation happened before we even had significant technology for mapping and localization. So we can also navigate in the presence of sensory impairment quite well. And Australia, in particular, has a long history of capable navigation. So the original inhabitants of this continent had very successful navigation strategies based on verbal and kind of musical strategies, which is very different from a traditional map. But nonetheless, it allows people to get around just fine across long water voyages as well. So in the natural world, animals famously navigate entirely, like very, very long distances. These are the migratory patterns of some birds, so this is planetary scale navigation, truly. Ants are very impressive as well, so they can do this kind of long, fractal type of foraging paths, going very far from their den, and then once they find some food, they can backtrack almost straight, in a homing path straight to the goal, to their home. Rats, also famous navigators, rats in a maze, including very, very complex mazes. So how do they do it? We won't fully address this question, but I propose that it's probably not by using an explicit map, although there may be elements to that. So we'll talk about some literature here. This is kind of the traditional approach for mapping, localization, and navigation. You have some kind of sensory input that you use to make a model of the world. You use these sensors to localize yourself in the world, some kind of state estimation, and you want to plan a trajectory and then execute that trajectory to achieve the behavior that you want. It's kind of the traditional approach. So potential field based local control, dynamic window, which is a stochastic local controller, or graph search methods like the A-star algorithm are popular if you have discrete state spaces. In continuous state spaces, you might use something like RRT. Now, these are kind of low-level control problems, short horizon planning and control. And this stuff has been studied for a long time. We have pretty capable kind of out-of-the-box solutions to this, as long as you actually have localization and mapping, some kind of way to know where you are relative to your goal and what obstacles might be in the way. Now this is a scene from this campus, and it might not be immediately evident, but this is a panoramic image, two different panoramic images of the exact same location. So you can see that this structure over here is actually the same structure as down here, and there's this large washed out image region that makes it very difficult to match any kind of detailed visual features here. So the problem of localization, even when you have a map or have reference images, is actually very, very challenging. So given the difficulty of individual image matching, sequential methods are popular. So this is kind of a sequential mapping approach where you have some observation. Well, you start actually with a kind of probably uniform prior or some more informed prior. You have some observation, but it might not uniquely identify your location. So what you do is you kind of disambiguate this with further observations and become more confident over time. This is a well-studied and effective approach. Now this kind of might have some parallels to how animals navigate. So rodents are well known to have these spatially sensitive cells in their hippocampus and related regions. And these cells reliably fire at particular intervals in the environment and locations in the environment. And over time, this can allow an agent to kind of fuse noisy, ambiguous sensor readings, visual inputs and whatnot, into a more reliable estimate over time. And in the RATSLAM work, this has been effectively kind of modeled inside of a robot for robot navigation by using an analogous procedure. So we have this grid of host cells, which kind of represent hypotheses about where the agent might be and what the orientation of the agent might be. And over time, this activity packet moves around based on local sensing and visual. And this is work by Michael, and produced some pretty impressive localization and navigation capability. But at the heart of that system was a kind of sequential filtering of noisy inputs. And Michael's next work, the SequenceSlam set of algorithms, boils that down to just matching sequences over time. Now what we have here is a confusion matrix. We have the ID of a frame here, and an ID of another set of frames that you're trying to match against. So you're kind of online trying to match against a data set of images. And the intensity here describes the image difference. So we're seeing, these locations are images where, when compared, have relatively high difference. These are pretty similar, or relatively low difference. These are pretty different images. But the important thing to note here is that while there's a lot of kind of good potential matches throughout this matrix, the best kind of consistent line of matches is down kind of the main diagonal there. So when you match based on sequences, you can actually draw a line and evaluate the matches along this line as a proposal for a velocity that you might be traveling on. And you can vary this red line, and at one point the line will intersect with most of these dark pixels. So that can give you a localization estimate, as well as an estimate of how fast you're moving. So that's the core of SequenceSlam. There's some really impressive results out of SequenceSlam. So you have these kind of day to night images. These are actually matching places, but despite the drastic visual differences, the system is able to match many of these. And it improves performance on this kind of challenging situation. Now this is a similar confusion matrix here, but what we have here on the right is the velocity of the two trajectories through the environment don't necessarily agree, so we don't have a straight line. And as you can see, any of these particular straight lines matching through this matrix are not aligning very well. So this paper by Ed Pepperell just allows you to normalize this matrix by odometry information, if you know how fast you're moving. And then you can fit a straight line to it much better. And they demonstrate really impressive day-to-night localization as well. Now, if you have localization, this doesn't necessarily give you mapping, but it can bootstrap you there. So this is what's referred to as a topological map. have this map on the left, which is metric and spatial, but the agent actually can build, the robot that you're driving through here can build a topological map, which isn't required to preserve global spatial information, relative transforms. Instead, you're interested in connectivity. And when it comes to navigation, being able to traverse an area to a goal is kind of your most important measurement. Where you are and how you might get to a goal. So this kind of map you can do basically just given localization and some way to know that you moved. Because when you get back to the same place, you join up the map. Now in RATSLAM, RATSLAM has been extended with a map like this. It's kind of semi-metric, but it's got a strong topological element. And the idea is that you can kind of back-propagate the gradients through this gradient of distance to goal through this map, and you can end up with kind of a local best path to approach the goal. So the thing is, this is kind of the traditional approach. And I've taken this slide from Vincent Van Hook of Google Brain, but I think it illustrates well the idea here. So in almost every field of AI, early on, you see these kind of modular pipelines that go from the input to the output you want, based on what we human engineers think is kind of the relevant, high-level abstractions to make for these problems. Now, in 2010, speech recognition was essentially completely, most of the work in the past could not keep up with these new approaches based on machine learning. You learn the features you need completely end-to-end. And you probably see where I'm going with this. This happened again in 2012 for computer vision and in 2014 for machine translation. Now all of these domains are completely dominated by deep learning, this end-to-end feature learning. So the question is, we haven't done this yet for robotics, but the question is this the next step? And we'll assume that maybe it is, and we'll look at what we could do. So this is a basic kind of toy diagram, but the idea is that classically in machine learning, you have supervised learning and unsupervised learning. Where supervised learning is about you have some kind of function you want to match. You want to reproduce the output of some ground truth labels, for example, and you can train your machine learning system to minimize the difference between its output and the ground truth. Unsupervised learning is just a loose collection of tasks and approaches where you don't have necessarily human labeled data, and you just want to minimize some other kind of objective, often useful for finding structure in data, learning representations without strong human labeling, and so on. So this is just maybe a recent example of supervised learning, state-of-the-art kind of system where you take input images. You want to produce a semantic segmentation map, so different kinds of materials and objects should be labeled per pixel on the output. And this is a kind of a classic deep learning architecture diagram. We have a bunch of interleaved kind of affine transforms with learned parameters with like activation functions in between, nonlinear activations. And this whole system composes an end-to-end differentiable function, so you can just train it to approximate the output that you want on your data set, and you hope that it generalizes to new points that weren't in your data set. In unsupervised learning, this is a recent example, where instead of having the desired output, specific output, what you want instead is just to say, these two images are reasonably close. We know because they happened at similar times. Whereas the blue image to the red image here, we know are probably not depicting something similar because they happened at different times. This is a video images. So the idea is that you want to learn an embedding, learn a representation, by pushing the representation of this image towards this image, while pushing it away from the representation of this image. And this is just a cheap way to generate some kind of labels and learn a representation. And in this paper, they then go on to use it for really impressive robot control tasks. But the thing that I'm most interested in talking about is reinforcement learning. It's been receiving a bunch of hype lately. This is the technique that we happen to use for our systems. And this is kind of one of the watershed moments in recent deep reinforcement learning, is where a team from Google DeepMind trained a end-to-end computer vision system to take in Atari input images and produce an Atari control signal from it. And it's learned with reinforcement learning, so this means purely from delayed signal of the score that you end up reaching. So some other, and this is the performance. It's quite good. So without going too into it, it's hard to see, but this line right here is human level performance. So on most games, this system managed to beat human experts at Atari. Similar for Go. So there's a game of Go. It's kind of like chess, but with very simple rules, but very complex consequences. And similarly, deep reinforcement learning system augmented with stochastic tree search was able to actually beat a human champion. So this is the world champion of Go at the time. He won 4 out of 5 games against the system, so it's quite powerful. And it's learned with reinforcement learning, playing against itself. Now, this exact same system was used to play against also with self-play. So it plays a lot of games against itself to improve. In other domains, these are all chess-like domains. We have Go, which I just talked about, but the system can learn to play Go. It's called AlphaZero. It can learn to play chess, and it can beat the baselines. Here is a baseline called Stockfish. It's an algorithm. And also successfully beats the baseline on Shogi, which is kind of a chess-like game. So it's a pretty general idea, and this reinforcement learning strategy allows us to learn very, very general behaviors, for maximizing all sorts of different rewards, including some real-world tasks. So this is from a paper called Qt-Opt, and what it does is given a large amount of real robot power and computational power, it can leverage that amount of experience to learn competent and quite complex grasping behavior purely from experience. So these robot arms kind of look down on this cluttered scene, and they reach down and pick stuff up. And you can even see that they've learned some emergent behaviors like pushing aside an object so that it can get at the object it really wants. It's really quite impressive, but huge amounts of data required for this stuff. So most applications, if you wanted to, tweak the task to run on a slightly different version of the task or in a different environment, you might have to train the whole thing from scratch, which most people don't have the resources for. So that's the kind of the background, but we want to apply this to learning navigation. Now, there's some precedent for learning navigation with reinforcement learning. This work by Murawski shows that you can learn to navigate a simulated maze using a recurrent reinforcement learning network and demonstrate impressive results. And then 2 years later, they extended this to learning street view environments. So they can navigate large-scale city environments without an explicit map as input to the agent. And it's really quite impressive. The only thing is, as with most of these reinforcement learning tasks, the evaluation is kind of done on the training set. So this was not deployed to the real world to see if a robot could navigate, although they did have some holdout goals that they used to validate. But the question is, does this stuff generalize to real challenging environments, like the deployment differences in the real world? Some more maze navigation examples. In this work, the agent learns to discover the goal and then repeatedly go back to it. And this is some preliminary work on actually deploying in the real world. So this is a target-driven navigation task where you're given an image of the goal you want to go to, and then over time, the agent learns to take movements in kind of like a very discrete environment in order to reach it. And this was tested with some basic but promising results in real-world scenarios, although they're just very small rooms with coarse discretization. But it's looking pretty good. So this leads me to what I want to address with my research questions. So the first is, if you want to localize against a single trajectory, what is required to do that in the presence of variation like velocity and route ordering? So as I talked about earlier, most of these sequence SLAM approaches end up fitting a straight line, which is easy to, computationally efficient to do. But it provides, you'll encounter some difficulties when you try to do things like match trajectories out of order due to city-street intersections. You can go down the blocks of the city in a different order. So maybe these fixed windows aren't appropriate. The second is, how can a procedure like localization and perhaps mapping emerge purely by optimizing behavior? So presumably, natural animals had evolution that these capabilities for them, but also the objective is to optimize behavior, as opposed to some kind of objective on high to do mapping. So can we get these to emerge as well? And then the question is, once we do that, once we learn behavior end to end, can we generalize this to challenging real world conditions of the sort that animals have to deal with? So we have some contributions toward this. So the first is a paper about relaxing the assumption of a fixed sequence length for sequence-based localization. This is published in RAL, Robotics and Automation Letters. The next is a paper about learning from a single traversal competent navigation strategies in an office environment with deep reinforcement learning. This was published at NIPS. And we have a third paper published in Coral, Conference on Robot Learning, which is deploying this system to a challenging large-scale environment with multiple goals and stochastic variation that we needed to introduce to solve the problems. So we'll talk about those in order. First, the question about localizing against limited data. So this is the paper. Here's a question. Are these the same place? And if so, why? Because this is a daytime traverse bottom and a nighttime traversal on the top. It's an omnidirectional image from somewhere in Brisbane. And the question is, are these the same place? If you were given these, could you tell? And it's pretty challenging, but if you look at a few different cues, this building and this building, you can see are actually the same building, despite appearance change, and these ones as well. So there's different lighting, and there's also some different viewpoint. And as we talked about, you can use sequencing to differentiate these, to be robust against individual difficult matches. And so that's what we're going to talk about today, with the case that's tackling routes that are traversed out of order. So here's an example of this, right? This is the Brisbane CBD. You can see that this long trajectory, maybe you need a certain amount of temporal context, a certain sequence window length in order to match this location. But in these areas, this is a short little section. This is a reasonably short section. Not the same. The same length of window doesn't apply equally well in every case. So we're going to try to address that. This is just it's hard to unpack, but the idea here is that these are two traversals of the same space, but they happen in different order. So this is one of the data sets that we're going to tackle. So here's a little schematic of what we want to do. So let's assume that this is a distribution of differences in images, right, along this axis, and how often you come up against that particular difference. And this, let's just assume we've fit a distribution, or we've measured a distribution. We have one image that we're trying to match against a whole collection, and of course, only one of the images in the collection is the correct match. So you can see that these are all incorrect matches. This is the correct match, and the correct match kind of gets lost in the noise of this distribution, right? It's not the best match, that would be this one. So you need to do some kind of temporal filtering to elucidate it. Now, if you have a suboptimal sequence length, if you're using perhaps too much context for your situation, then this is what might happen. The noise drowns out the signal and you match an incorrect observation. But if you have the right sequence length, then perhaps you can tighten the distribution of non-matches so that your correct match falls out as an obvious outlier. So that's what we want to do. We want to find the sequence length that makes the best match an obvious outlier. And this is some data for that. So you can see that along here, these are the distributions, the raw data and the distribution we fit using one of several distribution families to single image matches. So that's a window length of size 1. The idea is that individual image matches form a very Gaussian-shaped distribution, but it's very wide, very high variance. You can see that the best match is still got significant probability under that distribution. Whereas if you increase the window length, you can see that the distribution kind of becomes a bit more peaky. You can see some multimodality going on. But the thing is that as it becomes more peaky, you get these big outliers that stand out. And the question is how to find the window length that gives you the most outlierish hypothesis. So we phrase it this way. We want to find the sequence length that minimizes the probability of the best hypothesis under the distribution that we're fitting. So it's very simple. We search over a set of window lengths, I think 5 to 500 in this work, which is in line with the standard parameters in fixed length approaches. And the best hypothesis is going to be the one that is the lowest probability, so it's the most outliery in this distribution. So just to give you a visual idea of what this looks like, here is on this axis we have the window length, and on this axis we have the probability of the best matching hypothesis. You can see that no matter which distribution we choose to approximate this with, you see a sharp kind of trough here at the location which ends up corresponding to like the distance since a intersection, right? So the amount of temporal context that is truly important for this problem at this moment. So every moment we're refitting this number so as to always have the most confident hypothesis. Here's another example. The three different or four different approaches kind of vary a little bit here, but you can see they all agree that the appropriate sequence length is somewhere between 250 and 300, which is, and it is the case because a long trajectory with overlap is present in the reference data set. So this is a way to kind of visualize this. We have a confusion matrix where this is the image index that we're trying to match. This is the index of the images in the data set. So given every image, we have some kind of match on this matrix. Now it's a bit smeared out because we're now matching entire windows. And you can see here, the smear is more significant in locations with large window length. This perpendicular line, the blue, the trajectory, this line indicates how long the window is that is chosen. So here's another example where you can see that often the agent will encounter an intersection, the sequence length will grow up to use as absolutely as much sequence context as is important for the task at that moment until it transitions onto a new intersection, takes a different path. And that's the moment at which it starts growing those sequence length again. So we find that this effectively kind of keeps up with the movement in the actual environment. Now this is a lot of results, but the basic thing I want to show you is that lower is better, and we see that our approaches compete with kind of the best of the fixed length approaches. So lower. But the thing to notice is that while these are fixed window lengths, the ideal window length for some data sets is completely different than the ideal window length for some other data sets. And that's a thing that it's hard to know in advance without just trying a bunch of windows. So our approach, on the other hand, performs reasonably well, despite the data set. And the bottom row is an example where we've artificially shuffled the data set to reduce the reliance on fixed temporal context. So we've taken it out of order virtually. And we show that basically the same thing happens, but even more extreme. I should also measure the actual metric here. Actual metric is called the maximum time to localization. The idea is like how quickly can you match it? And when you come across around a corner, sometimes it's difficult for the sequence to accumulate enough to significantly match, and ours tends to match faster. Now the other metric that we're looking at is the area under the precision recall curve. It's just how well do you match, how precisely, and how many possible images do you actually match. And we can see that once again we're kind of above some of the choices of fixed window length, so we're a bit more robust. So that's all well and good. That approach kind of improves robustness to these parameters, but ideally, I guess we could relax more than just the fixed window length. What if we relax the concept of explicit localization at all? Maybe these things can emerge by optimizing behavior. So that's the topic of the second paper. And so just to bring back this work, this is navigating large cities on the basis of images in kind of a graph-structured virtual environment. The thing is that they never deploy this in different conditions. They don't see how well it generalizes because they have just one street view map to work with, and deploying in the real world is expensive. So we want to see if we can take this idea but deploy it on a real world. Now this is their training curve. The details aren't that important, but I want to draw you to one thing in particular. That means 1 billion time steps of training experience. And in their environment, of course, that kind of equates to one kind of real step of the agent taking an action in this environment. That would be like 31 years of real experience, which is a bit too much for us to just deploy this, on a real robot, obviously. And a real robot is what we want to work with. So we have this robot here, and our proposal is to map an environment with a very simple, very lightweight style of mapping to just drive throughout the environment. This is the very cantina, or the room the floor that we're standing on right now, and this up here is kind of the cantina area. So we drove this robot around, and then the minimal amount of human annotation we need here is just to indicate where the intersections are in the environment. So drive this thing around for 5 minutes, click 5 times, pretty lightweight, 6 times. And then the action space that we use, I should say also, each one of these nodes is associated with an observation, right? An omnidirectional camera image. And the goal of the agent is to traverse this graph to reach the single goal, fixed goal location. So from any initial location, try and reach this goal using these 3 potential actions, moving around virtually. And the images are not great quality, and they have some differences. So this is Adam Jacobson, and he is standing in a location where he was not standing in the training data, and that means that this has some visual differences that are sometimes hard to compensate for. There's also, you can see a bit of viewpoint change here, maybe some lighting change. So the question is, how do we be robust to that when we evaluate on the validation step, which is a completely different recording of the environment. So we have 2 stochastic augmentations that we do to this data. One is to sample candidate observations from a nearby window in the training data. The other is to randomly rotate them by up to 8 degrees. So these are 2 ways of gaining viewpoint invariance, or some degree of it, by explicitly including them in the data set. This is the architecture. The most important thing to note is that we have a recurrent policy, and it's training to optimize a reinforcement learning objective. And we have these fixed, pre-trained visual encoders, one for each 90-degree view in the Omnicam. And that turns out to be important, so I'll show you why. So this is the validation performance. We take the minimum across the pool of workers, which are like parallel evaluations, because we want to know the worst case behavior of the system. And we can show that with these stochastic variations, we get better performance on the validation set, which is another recording of the same environment done on a different day. This is the deterministic version that just delivers the same observation to do. We also measure the ratio of the validation performance to the training performance. So if you do pretty well and you're transferring well, you'll have a value near 1. So we see pretty similar performance on the validation set compared to the deterministic version, which doesn't seem to get any. Now, the other thing we evaluate are the learned pre-trained visual features. So for one thing, training on a few thousand images in this data set is difficult to learn generalizing visual features from. So we found that having fixed pre-trained visual encoder, this is up until the pre-final layer of a standard ResNet architecture, which is a state-of-the-art kind of computer vision network for classification tasks. So we have a pre-trained version of this for object classification. And using these features as input, we find that the system learns better. It overfits less to the visual situation. And we can once again measure the relative performance. So it makes an even bigger difference than the determinism. So that's what we see in this case. Important to note, it's not that it learns a lot faster, but the thing is that this is all simulated experience. The real data that I needed to collect to build this environment and run it took about 5 minutes once we, worked out the kinks. So it's pretty cheap, and it allows us to take a single experience and turn it into a competent policy to reach any goal that we want that we select in the training time. So, but the real question is, this is a validation data set. It's still a fixed kind of graph-based model, virtual model. To what degree can this thing that we learned actually generalize to a real deployment? Large scale, reaching multiple goals, not just one, and on a real robot. So that's our next paper. So this is published in the Conference on Robot Learning, and we tackle exactly that problem. So This is the analogous graph for this paper, which is a much larger situation. You can see that the entire graph that we included on the previous work is this little bit right here. So we've scaled this up significantly to include 3 more floors from this building, 3 floors from O Block, which is another building on campus, and most of the robot navigable kind of pathways on this campus. I was also going to do the gardens until someone told me that might not be allowed. But we probably could have done it. So it's a really large-scale environment, and we want to deploy this actual robot here. And once again, this is some imagery from that. So you see the same difficult conditions, the washing out of the visual features. It's going to be quite a challenge to deploy under these situations. There's some big changes in shadows and sky. We got raindrops on the lens in this run. We got it back to the lab before it exploded. And the most challenging obstacle of all is people who just get all up in your way and they don't understand what a robot experiment is. But that's great because we managed to actually cope with it pretty well. So they're challenging visual situations. So once again, we have the same 2 viewpoint invariance style augmentations. We also add, for this work, independent pixel noise. So we sample independently random Gaussian map that we add to the image. This kind of models small fluctuations in the brightness of individual pixels, which occur just with regular low-quality cameras, and changes in lighting and reflectance and whatnot. We also add what's called Ornstein-Uhlenbeck noise. This is temporally correlated shifts, and we apply this globally to the image. So if you've ever worked with computer vision for robots, you probably have to consider the idea of auto exposure on your camera. Fixed exposure is nice because you kind of have repeatable imaging, but it means that if you have too much light in the scene, you'll wash out the pixels. So often we like to use auto exposure. It's just that causes these kind of shifts in global brightness as we traverse the environment and change our lighting conditions. So that models local noise, global kind of noise, and the one last thing that we add in this version is we add a small probability of a failed action. And what that means is that anytime you take an action, nothing might happen. This is important because, in principle, this navigation agent could achieve perfect performance by looking at the single observation and goal image at the start, and then executing an open loop trajectory. Right? This is actually a problem in the Atari-based systems when you have a fixed set of initial conditions to work with. The agent never learns to generalize to different situations because it always just takes the best trajectory over time. So we want to avoid reliance on that because when we deploy in the real world, there will be differences in actuation. Right? We won't drive forward the exact same amount over time. So these 5 sources of stochastic observation allowed us to transfer to the real world. Now this is the architecture this time. It's pretty similar, although I've expanded the ResNet here. We're using ResNet 18, which is just a smaller model than the ResNet 50, but same idea. We then extract from these fixed layers, we don't train these, a 4096 dimensional fixed vector for the observation and an identical one for the goal. So we pass in an image of the place that we want the agent to reach. And then this goes through kind of a standard reinforcement learning architecture known as asynchronous advantage active critic, which was the state of the art at the time. It's recurrent once again, so it can fuse information over multiple time steps. And it takes the goal lesson, which is different from the previous system. It also makes it a lot more challenging because you don't only have one task for every individual location you're at, but also every pair of locations and goals. So it's kind of infeasible to memorize the whole thing. Now, this is kind of what the system looks like. We have an observation, we have a goal. These are those images and observations and goals as represented by the dense feature vectors from the ResNet encoder. So it's just kind of some positive and negative values in a long vector. And this is the graph that we're building, or that we've built up here to navigate. You can see here the probability of the different actions taken by the agent. Now there's move left, go forward, turn right. But then we also have these 7 additional mystery actions, which these are actually elevators. So the thing is, this is now kind of a 3D environment. We have to go up and down elevators. But the problem with that is that if you just have an up and down action, that means kind of infeasible. Instead, what we have is a target floor for every possible elevator traversal. This was kind of one of the really gratifying parts of this work, because while sometimes the agent made a few mistakes while traversing the rest of the environments, when it gets to an elevator, it knows exactly where it wants to go. It's like high probability every time. I think it's like visually distinct and whatnot. And it's a high consequence action to take, right? Because it changes the observations completely, which changes your value estimation for reinforcement learning. So it's like, I think there's a lot of weight on that particular thing. Anyway, it's great to watch. But this is a part that will be almost impossible for you to see. Is I've highlighted these nodes in light blue that are allowed as goals for the current level of curriculum. So this is an important mechanism for us to actually learn this goal-directed policy, which is like much higher in combinatorial complexity than the single goal policy. What we do is we start the course of training only sampling goals that are very close to the current location of the agent. So when you spawn it, you choose a random location, you choose a random goal in a small region. And then we ensure that the agent gets up to, I think, about 90% performance before we increase the curriculum. And then you can see, if you can at all, there's kind of a wider radius of potential goals that we can sample as we increase the radius during training. And by the end, we have a radius that includes pretty much the whole campus, and the agent has maintained pretty consistent performance the whole time. Now, we found this was very important. It's too hard to learn this thing kind of flat without that mechanism. We investigated like hierarchical mechanisms, and there's a thing called hindsight experience replay that allows you to reuse trajectories as if they were goals. None of these seemed to tackle the problem, but as soon as we did the curriculum, it works. So if you encounter problems like this, curriculum is a good solution. Now this is what the training curves look like in simulation. This is, we evaluated 3 different visual front ends. This is completely randomized, untrained content. The same architecture as the ResNet 18 that we use. There's also versions that were trained on ImageNet in blue, which is object classification. And then there's one in green that was trained on Places 365, which is actually kind of place categorization. So given an image, is it like a beach or is it a parking lot or whatever? And this, the 2 of them perform pretty well. I think they would probably both deploy equally well. But we chose the green one because it's just tiny, marginally more performant than the ImageNet version. And in principle, localizing places might, or categorizing places might provide you with maybe some more relevant features for this task. Anyway, this is some evaluations. So this is the real robot acting according to its policy. And here you see, almost impossible to see, but I've overlaid the actual map on here. And this is the shortest path from the start location to the goal. This is the path that the agent takes during training, so as in on the virtual environment to get to the goal. And this is the path that was taken on the actual robot when we went out and deployed the system. So you can see that the path, while it's not identical to the simulated trajectory, it's very similar. There are a couple of mistaken turns here. You can see also that the system kind of turns around and goes back several times before successfully getting there. So it's not perfect, but it's pretty high-performing path compared to the alternatives, such as this one. So this is another trial that we did 11 in total. This is the optimal path. You see that in simulation, the agent takes a path that's pretty close to optimal. And then in deployment, there was some kind of maybe visual appearance change, localization issue, where the agent kind of went around this big long loop before successfully recovering and then reaching the goal. So effectively, it was just going in the wrong direction and failed to recover until it came back. But this was the second longest path. Now the longest one is this. So this is the one failure that we had, where optimal path taken in simulation, but then up here there is no reaching the goal at all. So it kind of just went around in circles. If you look at the images, you can see that it kind of goes down this path, turns around, goes down again, turns around, and then ran out of batteries. But the important thing to note here is actually this is the part of campus, this is kind of a qualitative distinction, but this part of campus was the part this was in the afternoon. So this is the area that is receiving the highest amount of direct sunlight, and it was recorded at a different time of day. So this is truly one of the biggest appearance changes that you get from kind of month to month here. And this is, remember I showed you an example of like a washed out camera image that's really hard to tell. That is from this trajectory. So the hypothesis is that this is maybe due to the difficulties of this one. But 10 out of 11 of our trials were successful. You see here I'm plotting the optimal, so this is the optimal length for a particular start and end location. This is the actual length taken. So the red curve, the red line is if you were actually executing a policy. You can see that our agent in the training data, the training environment, does quite well. It's, there's a bit of a tail off, but most of the time it's sticking close to the optimal path. And these are our deployment experiments here. Most of them are clustered around the performance of the agent during training, but there are a couple of outliers that got confused into one paths. Now this is a different view on the data. It's the ratio of the agent's path length to the optimal length. So how much worse in path length is this trajectory. You can see that it's clustered heavily around one, and the deployment experiments that we did were kind of sticking close to the performance of the agent with notable exceptions. Now this is the raw data. Without digesting it too much, I think this is the important thing to note. On average, our deployment trajectories were about 2.5 times as long as the optimal trajectory for that pair of inputs and goals, which is certainly not perfect. But the question that comes to mind for me is, what are we actually looking for here? Perhaps optimal navigation is what we're after. Humans, on the other hand, are very rarely optimal in any way. So perhaps reinforcement learning will get us a satisficing solution without necessarily being optimal, but maybe more training, better monetization. These are all the deployment trajectories. We see that we have a single goal here for consistency, but we start from many, many different trajectories. We cover most of the space of the campus, and all except for one successfully reach that goal. So the question I asked was like, can we learn localization end-to-end through behavior? And this is what I'm trying to answer here. What we did is we froze the weights of the agent, so we're not training those. Then we trained just a linear classifier to predict which location the agent is right now from its recurrent internal state. Right? So we want to localize from the representation that we've learned. So you can imagine that perhaps this representation is doing some kind of sequential filtering. So we found that on the training data, this was able to correctly predict the location pretty effectively. On the deployment data, you can see that there's signs of this working. So the agent is actually there. The hypothesis is kind of spread out around the graph, but the biggest location is truly in the right location. So this is evidence that maybe some of the performance loss during deployment is due to localization errors because it's kind of less precise. But what we're really interested in this investigation is like, does this curve go down? This is the entropy of the localization distribution and the entropy of the policy, so what the agent wants to do, against the time step of the environment, time step of the episode. How long have you been watching the environment and navigating that? And we see that there's this sharp decrease in entropy at the beginning of episodes, followed by a continuous decrease over time. So this kind of is evidence that the agent is becoming more certain of its location over time, even though the agent is not being trained explicitly to predict the location at all. It's purely for purposes of behavior, reaching a goal. Now, of course, knowing where you are, pretty useful for knowing how to get to a goal, but it's reassuring to see that the evidence seems to suggest that this is happening. So I just want to conclude, animals and humans are great navigators, much better than any current robot that we have right now. Very challenging situations to flexibly navigate the world. We can explicitly localize and map, and this is useful if we want to explicitly control and plan, for example. But perhaps we can learn these things implicitly through just learning tasks end to end. So our contributions are the adaptive sequence length method, learning to navigate from a single traversal, and then showing that we can deploy that at kilometer scale. Limitations. This sequence slam method that we developed for adaptive winnowing still kind of assumes some velocity compensation. So even though it can handle route traversals out of order, it doesn't automatically curve those lines that we see in the confusion matrix. And although it provides probably a little bit of robustness to that, it's not the full solution. Also, these graph-structured models that we use to train our one-shot reinforcement learning agent might not actually apply in all domains. So graphs, sparse kind of connected topological maps are perfect for navigation. They're kind of the minimal amount that you might need to get around if you're using map at all. Now, in a situation like manipulation, for example, high-dimensional continuous situation, maybe a discrete graph-structured map of that environment is a lot harder to make. And the other problem is that our high-level environment does not express low-level control. So the agent is not executing its motor commands through this environment. It's choosing to move to the next node, kind of like Street View. Right? So that is difficult to express directly in a topological map. So a bit of future work to address these. I think that the sequence SLAM approach can be leveraged while not providing too rigid of an algorithmic structure by just learning to localize end-to-end with recurrent representations. So this here is some work that shows that you can take an image of a top-down, satellite imagery of a place, and take side-on imagery of a place, and train a representation that is similar for the top-down and the side-on views. You can use this to effectively localize against images that aren't even from the same kind of coordinate frame as you are. So can we leverage this maybe to learn representations that are recurrent, that do the similar kind of thing? So given a bunch of observations, we want to have a recurrent representation of that sequence and that location that is close to similar locations, even despite different work. So maybe that'll be a more end-to-end approach to the problem that our paper solves or addresses. Now, this is some work that shows that maybe you can learn a low-dimensional embedding in which to build a graph-structured map. So space is nice because it's already kind of low-dimensional, and you can build maps in it reasonably easily. If you're mapping in some high-dimensional, like image space or manipulator space or something, that might be a little harder. But in this work, the authors learned to map from, or to project from image observations to I think three-dimensional latent space that you can see almost already resembles kind of a topological map when you trace a trajectory through. So you can imagine using that to extend the same kinds of ideas that we have to harder domains and more high-dimensional implicit, where the intrinsic space is higher dimensional. Now, the other question is how, given only a high-level simulator, do you produce an agent that can produce low-level velocities? Low-level velocities are interesting, right? You can learn to take certain paths that better localize you. You can learn to avoid pure rotations, stuff like that. But our algorithm, our environment doesn't really express that level of resolution. So my proposal is that you can take something like this, which embeds trajectories in order to do a multimodal kind of matching thing. We could do that in order to embed a trajectory that you can then decode into raw actions. So at the high level, your agent might be learning in the space of high-level trajectories. At the low level, you can still decode these into raw actions. So that's maybe a potential direction for this. But that's the end of my confirmation, or final seminar. And yeah, any questions are welcome.